Hello everyone, and thank you for coming to this session where I will present to you RoboPisces. RoboPisces is an Erasmus Plus project where partners from Italy, Ireland, Latvia, Greece, Malta and Croatia are participating in order to investigate and develop innovative educational robotic strategies for primary school experiences. The educational robotics creates an attractive learning environment by keeping students interested and motivated with hands-on, fun learning activities. RoboPisces aims to create a teaching and learning curriculum based on educational robotics through a constructivism educational approach and the design of a toolkit called RoboPisces, as you can see here in the picture. We want to engage primary school students with the purpose to enhance the learning outcomes in STEM subjects. So within the first year of our project, we have actually worked on a curriculum in order to work with the standard basic toolkit for the teachers. In the second year, we plan to have a more advanced toolkit for the teachers. So the FIS curriculum, as you can see here, there is different components, but today you're going to hear a video and get a glimpse from the sample of curriculum that we have created. As you can see, within the FIS curriculum, we start from basic concepts of robotics disciplines and we end up with more advanced concepts within marine robotics.
Welcome to the second topic of the RoboFish curriculum, the Robotics Disciplines. In this topic, you will be presented with some basic consideration about what it takes to build a robot. You will be prompted to reflect on the scientific disciplines involved in the robot design, building, and programming, to understand the role that science, technology, engineering, art and math play in robotics. You won't need any material for this lesson of the online course, but you may need something if you're willing to explore this lesson with your students. Let's start. In topic 1, we have already talked about the production process and the jobs in the robot industry. We saw that there are many skills that a roboticist should have, both hard skill and soft skills. Regarding the hard skills, we are talking about the foundation of robotics, the classical disciplines involved in the production of a robot: computer science, mechanical engineering, electronic engineering, and automation engineering. We already saw that nowadays, to build more efficient and socially acceptable systems, many other disciplines are contributing significantly. But let's focus on the disciplines that enable this technology breakthrough. These 4 disciplines are the ones we cannot do without to build, program, and manage a robot. Very often, we hide them under the acronym STEM. For example, technology is the generic term to say that we are using the best motors and sensors, or that we are employing the safest and most reliable materials for the robot structure. Science discoveries on semiconductors has been necessary to exploit them in the robot brain and circuits. There is also a lot of math around the control strategies of a robot, as the brain of the robot thinks in terms of parameters and variables. The brain of a robot is reprogrammable, which means that teams of expert software engineers can translate the action we want the robot to perform into instructions in the language which is understandable by the robot. Robotic technology represents the hard sciences accomplishment, the so-called STEM. Let's try to understand something about the fundamental knowledge that leads to the artificial life. Electronics deal with the emission, flow, control, and storage of charges in a medium. We can see that a robot or any tech device in our hands has one or more printed circuit boards, PCB, filled with electronic components. Maybe you have heard of the Arduino board or Raspberry Pi board. They mechanically support and electrically connect electrical or electronic components using conductive tracks, paths, and other features. Components are generally soldered onto the printed circuit board, called in short PCB. Soldering electrically connects and mechanically faster components to boards. Electronic engineering is a relatively new field. Even if static electricity was already known by ancient Greeks, who knew it as a feature that came out from rubbing fur on materials like amber, it was not until 1948 that the electronics industry was revolutionized by the invention of the first transistor. And we have to wait for 1959 for the integrated circuit chip and the silicon metal oxide semiconductor field effect transistor. Before that, electronics was linked mostly with telegraphs, telephone, radio, and television. To gain a full understanding of modern electronics, one should have a solid knowledge on advanced math, physics, chemistry, and materials. For example, an electronic component is the light-emitting diode, LED. An LED is a semiconductor light source that emits light when current flows through it. A semiconductor is a piece of material which is characterized by its property to make electrons flow. Some examples of semiconductors are silicon, germanium, gallium arsenide, and elements near the so-called metalloid staircase on the periodic table. The recombination of electrons and electron holes in a semiconductor produces light. Physics and chemistry of a semiconductor may be beyond the primary school curriculum, but maybe this may trigger a reflection on the devices we are surrounded by. Do we really know how they work? Can we really tell the differences between an electronic bulb and LED? A robot has a mechanical structure that is functional to climb uneven grounds or to fly or grasp an object. To design a fully functioning robot, we have to rely on a solid and well-organized structure. Physics and science of materials are fundamentals to study the motion of a single part with respect to the others. Of course, math is needed and an advanced skill set in systems thinking. Just think about the motion between two gears. The transmission of rotation between contacting two wheels can happen only if the teeth profile perfectly combines. Moreover, their motion is tied one with the other. There is a specific ratio ruling the relations of their velocity. This mechanism is to be found, for example, in the transmission of the motion between motor and wheels. Control strategies are needed to achieve the desired behavior. If we want the robot to move from a point A to a point B in the space, we need to define how the robot is going to do that. Define how means that we explain the trajectory in terms that we can apply it to the robot. For example, to make the wheel go forward 1 meter, we can say to the robot, perform n rotation of the wheels, because we know that n rotation of the wheel corresponds to the repeating n times the circumference of the circle that may represent the wheel motion on the ground. This is a strategy, an open loop strategy. If we would have had a closed-loop strategy, we could have measured this given distance, and we would have stopped when the sensor provided the distance of 1 meter. To control something, we should have a mental representation of the real system and a way to manipulate some part of the system I am interested in. The mental representation is called the model of reality, and we can further represent it by means of mathematical formulas. Software is a collection of computer instructions that tells the system how to work. By contrast, physical hardware physically builds the system and actually performs the work. Software allows us to program the robot to do something. The more the robot is rich in sensors and actuators and joints and degrees of freedom, the more complex the control system will be and the harder it will be to translate the control strategy into line of code. Actually, software is not only responsible for providing the instruction to the robot, it is also what the interface to program the robot on the PC is made of. Every laptop, tablet, and smartphone have software inside them to produce the interfaces we all use. For example, opening a window on the desktop means that we are interacting with the PC program, which is a specific piece of software that interacts with the PC user. If we are opening the browser, it means that we are launching an application on our PC which is made of code. How many other examples of software we interact with can you think of? Another interesting fact is that we can write software on paper before even getting our hands on the computer. We can use the flow diagrams to represent the set of instructions we are going to write in our code. Can you use the flow diagram to represent the sequence of instructions to make a cup of tea? As we already saw, other than the disciplines we have seen, there are many other disciplines that help develop robots. They may represent many other opportunities and paths that a student may follow to gain interest in robotics and in education.
Thank you for listening. I hope you enjoyed the sample of the curriculum. As you can see, these will be our more advanced toolkits that will be used in the schools. And hopefully next year we will see you face to face and we will all try the RoboPisces in the Still Lake. Thank you very much.